Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. And good afternoon, class. This time around, we have to do our SIC 1004 virtually because of some timetable clashes. So anyways, this time around, I'd like to sum up everything on what we have learned so far. We start first by scanning your attendance here. Now, because this is a sum up of everything we have learned, so I'm taking the gist of what we have learned so far, of all the weeks that we have covered. But please, when you're revising, do not only focus on these slides, please look also at the core lectures. So really what I've done is taking excerpts from each lesson slide and brief on it and give you an overall picture of what we have covered. And hopefully by doing this, it becomes clear to you what we have covered so far. So the first thing that we started out with was to introduce to you on what a system is, surroundings, and what actually goes in between them is actually a boundary. And with the system, we have three main systems that we define, mainly the open, closed, and isolated. And each of this comes with definition on whether the mass, work, and heat actually interchange between the surrounding and the system. And we need to describe what is the system, okay, the entities that define the system. And so we have two main properties to define the system, the entities, the physical entities, and you have two types, one being intensive and one being extensive. And this, whether they are intensive or extensive, depends on whether they are mass dependent. Okay. Right. The PV diagram is the essence of this thermodynamics, especially in the first law of thermodynamics. The four main processes that we described were isobaric, isothermal, adiabatic, and isochoric. Isochoric means isovolume. And we have this PV diagram to describe the work that entails. And the first law that we introduced was the zeroth law of thermodynamics. And in essence, what this law actually explained was that if two thermodynamic systems are in thermal equilibrium with a third one, that means they're all in thermal equilibrium with one another. In essence, this picture shows that if A is equals to B and B is equals to C, automatically that also means that A is equals to C. So there we have the zeroth law of thermodynamics. The first law of thermodynamics concerns the conservation of energy. Here is the expression that you were introduced. Delta U is equals to Q plus W. What this talks about is, how much actually of this internal energy goes to work, how much actually goes to heat. And of course, in an ideal world, you want 100% efficiency, in which you have 100% work. But unlikely that's going to happen. In this part of the first law of thermodynamics, you're also introduced to the fact that the signage is also important to signify whether the work is done on the system or work done by the system. And so the signage means whether it can be positive or negative accordingly. At one point we talk about the state functions, and really state functions are actually the opposite of path functions. State functions, a state function is independent of path. That means what is concerned is only in the initial state and the final state. Here you have two paths to actually reach Mount Kinabalu. One is A path, one is the B path. B takes a harder, further distance and work. But in terms of the initial and the final state, it's all the same. So state function, doesn't matter how you actually reach that, it's actually in the initial and the final state. Is important. So work is very important because we want in a system maximum amount of work is done. So that sort of like describe the efficiency of a system. Work is equal to minus P delta V. And in terms of the PV plot, so we have here a cyclic process, which reminds us of a Carnot thermodynamic cycle. So we have the isobaric, the isothermal, isovolumetric or isochoric, and adiabatic processes. And the shaded areas signify the work done. And so this really reminds us of the Carnot cycle, which you have this. It's a thermodynamic cyclic. It's an ideal thermodynamic cycle, which talks about efficiency. The specific heat capacity or heat capacity is one where we measure how much heat is required to actually increase the temperature by 1 degree. Whether it's specific heat capacity, which depends on the mass, or the molar capacity, which depends on the per mole. It depends, at the end of the day, it depends on what the unit is. And this is covered in one of the lectures where we talk about the heat capacity. And one of the things that we talk about is what is the difference when you have this condition in which the setup is set such that the volume is constant versus that when the pressure is constant. Now, according to the first law of thermodynamics, at constant volume, no work is done, and so all the heat will actually goes into changing the temperature. So in other words, when you're working at constant pressure, some of the heat goes to changing the temperature, some goes to work. So you have that balancing. But for volume, everything goes into changing the temperature. Hence, it will take less heat to actually produce a given temperature at constant volume. So you don't need so much at constant volume. Of course, we like to make a relation between the two C's, CV and CP, and the relation is as such. We take it from the ideal gas law and we incorporate that into our main equation, which is actually the first law of thermodynamics. And from there, we condition them, whether it's a constant volume, and we get this relationship which says that Cp is equal to Cv plus R. So before you actually take this as the final expression or equation, please look at all this simple equation, but learn how to derive this. Of course, the details are actually found in the actual series of lecture notes that we have covered. Enthalpy is a state function, and at normal atmospheric pressure, where we work on a condition when pressure is constant, delta H is equivalent to the heat given off. And so, because it's a state function, the standard enthalpy of reaction, of any reaction, is equivalent to that of the products, to that of the reactants. Right. Then we make a relationship between enthalpy and the internal energy. So we have the first expression, which is delta U equals to Q equals to W. And because W is given as such, and delta H equals to as such, and assuming that we have an ideal gas condition, so the final expression we get is delta H is equals to delta U plus delta nRT, in which delta N is equivalent that to the number of moles of gas for the product minus that of the reactants. The next question that we actually asked was, when is delta H equals to delta U? It doesn't take, so long to guess by looking at this expression. And it's quite obvious when delta H is equals to delta U. If that is still not obvious to you, go figure, okay? It's all in the lecture notes. Nothing surprise. The Carnot cycle describes this hypothetical, this theoretical thermodynamic cycle, which consists of the isothermal expansion, because you have increasing volume, adiabatic expansion, then you have isothermal compression and adiabatic compression. This suggests that you actually end up where you actually started with. And this is sort of like the ideal, of getting a maximum efficiency. So this is, of course, a theoretical thermodynamic concept which was formulated by Sadi Carnot. We are moving on to the second law of thermodynamics. Now, remember that the first law talks about the conservation of energy, where you have the internal energy being Q plus W. So you have that work which you want. But then, where does the heat actually goes to? What happens to the heat? And so this brings us to entropy, okay, which suggests that this heat flows from hot to cold and gas flows from high pressure to low pressure. So the second law of thermodynamics says that the entropy of an isolated system increases in the course of a spontaneous change. Well, I like to think of this in the finer definition, because the second law also talks about the prediction of the direction of the process, okay, in which direction is the reaction spontaneous. And then it also talks about the establishing of conditions of equilibrium, whereby the ultimately the equilibrium state is being established. It also determines the theoretical performance, the efficiency of the engine or whatever process that you have. And so that's what second law of thermodynamics actually talks about. And so with the being given off, that defines what happens if it doesn't go to work. It's part of the entropy. And so delta S is equals to that dq over t, the integral of that. Having said that, because there's a relation between delta H and Q inside a phase transition, you have that expression that relates to the entropy. Now, in the isothermal expansion of an ideal gas, we can also expand this to relate that with delta S, and that gives you this expression. Okay, so I hope that this part of the lecture really helps, because if you think that it's a lot of equation, so I am seriously concise concising everything so that this becomes much clearer to you what we have covered. And that's the motivation, and that's what I aspire to achieve for this lecture. And we'd like to talk about relationship. So what is the relationship between entropy and the heat capacity at constant volume and constant pressure? Ultimately, this is what you're going to get, the expression. How do we get this expression? Please look at the relevant lecture notes. Now, the third law of thermodynamics was probably the best part of the lecture, except that I was frustrated. There's no sound effect. Or my aircon was cold, still cold, especially this time of the year. So imagining that it's cool, so we can imagine, or probably hope to imagine, that you can imagine, I can imagine, that at absolute zero, delta S, S is also going to approach zero. So when everything is just rigid and not moving at all. It's a state function, and hence you have the product minus that of the reactants will give you the standard delta S. What happens to the free energy that we want to, translate into work? We have two. One is Gibbs free energy, and this expression is given as delta H minus T delta S. What the signage, whether it's negative, zero, or positive, it means that it's spontaneous in the forward reaction when it's negative, equilibrium when it is zero, and spontaneous in the reverse direction when it is positive. Of course, as I've said, it is not just about that. It also talks about, if you're thinking about financial-wise, is it economical to do the reaction? This can also be a guideline. If it's negative, so it's something that is worth investing. Thermodynamically, it is possible to have this reaction go forward. But what if you have a positive delta G? Does it mean that it's not worth investing? Well, this is only true thermodynamic. So perhaps kinetics will be an answer to this. So is it possible to actually do a reaction if the delta G is positive? So that's something that I wanted you to think about, and I still want you to think about. Now, it's also a state function, so delta G standard is equal to that of the products minus that of the reactants. Then we have another free energy, which is the Helmholtz free energy, delta A, which is equivalent to maximum work. And here, delta A is equal to delta U minus D delta S. In case you were not paying attention, delta G is equal to delta H minus D delta S, or that of delta A is equal to delta U minus D delta S. How did we get this expression? Well, I'm going to say it again. Go look at the lecture notes that talks about this, okay? Now, delta G doesn't only describe the spontaneity of the process, ultimately it also describes a non-expansion work, like an electrical work. So we call this additional work or non-expansion work. And that delta G and delta A can also be related via the ideal gas behavior, and ultimately what you get is delta G is equals to delta A plus delta nRT. Right? Now, what I've just done was recapping everything that we have done so far. So now let's recap what we have just covered. Okay, so recapping what we have recapped, sort of. Okay, so the laws of thermodynamics. Okay, if the two thermodynamic systems are each in thermal equilibrium with a third, so that they are actually equilibrium with one another. If A is equals to B, B equals to C, hence A equals to C. So you sort of like know the direction of heat flow. The first law talks about the conservation of energy. So you can't create, neither can you destroy. And so that's what this first law of thermodynamics actually describes. And so, of course, in reality, this poor guy says something about his mother-in-law. He didn't create, neither can he destroy. Haha. And the second law talks about what happens to that amount of heat that's not translated to work. And so that goes to entropy. And well, that also describe the fact that you cannot have 100% efficiency. So you have this disorder, this randomness. So in reality, there's always entropy in my house with the kids, with their toys, with their books. So I can really relate this picture very well. So how random is your college room, your dorm room? You could probably relate that. Well, I hope you're a neat person. Anyways, the third law. Well, we can imagine America is cold, and it's definitely cold. 9 months of being in a cold weather. Now, and they sort of like, the inhabitants there probably get used to the weather. Their body probably regulates to that. Their biological system probably regulates to that temperature. But in the lab, it is always a constant inspiration, desire to actually achieve absolute zero. Because in a myocon, that's far from being what you call absolute zero. And still we find it really, really very cool. So this is quite a while. And think the latest achievement is not too far from this value. And the desire to do this is because it will create a no resistant electrical current. And this is good, for example, in spectroscopy, where you have the superconductors and your instrument is going to work super well. Okay, but that is at the lab level. So in reality, Jack died frozen in this North Atlantic Ocean, and the temperature when Titanic actually sank was about -2 degrees Celsius, and these passengers couldn't survive long in that temperature. So really, the reality for us is going to be tough if you're not used to, but this is just for you to imagine what cold is and how that affects entropy. How many times did you watch Titanic? Have you watched Titanic? Anyways, I remember this movie coming out when I was an undergraduate like you. So this has been quite a while. Now, let's talk about take-home exam. But first, let's talk about next week. Now, because Monday will be taken by Prof. Sharifuddin, so we will have our last class next week on Wednesday. And on Wednesday, our class will be at 1 p.m. during lunch break at D129, which is at the old chemistry building, which is in front of the main office. So Wednesday, next week, our class is there. and only then the take-home exam questions will be distributed. Absentees with no valid reasons will not receive a take-home because this take-home be will not be put up in Spectrum, and the take-home will be due on Friday. So you have 2 days, 3 days if I were to include on the 18th, and they are to be submitted at my office by 3 p.m. No later than 3 p.m. So, and during the class on Wednesday, we will do some tutorial questions, and the questions will be presented, will be put up in Spectrum this week soonish. I'm working on it at the moment. So having said that, when everything you studied on the exam, the lecture notes and the textbook will give you a big hug. And I hope this happened to all of you. Okay? Alright, so that's it from me. And please scan your attendance for today. Thank you, and Assalamualaikum warahmatullahi wabarakatuh.